Okay. So yeah, so let's get started here. As you can see here, yeah, welcome to the first meeting of a workshop that we're entitling Machine Learning Primer. I realized it might not have been specified, by the way, in the email that was sent out before. I am practicing my French, but I'm going to be presenting all in English here. So I'm sorry if that makes it slightly less accessible to people. So of course, if there's any questions or you need me to clarify anything, I'll do my best by slowing things down in English, because my French will not probably help you at all on any of that. Also, I want to let you know this is session 1, as you see on this first slide. The intention right now is for me to do a total of 5 sessions of this workshop. So we'll start off today with looking at topics that are sort of more introductory. We'll look at some dimension reduction techniques as well as clustering techniques that might be somewhat familiar to you. And then we'll go on to a more general framework of how we perform data modeling, different data types, as well as loss functions and how we might evaluate models once we train them. There we go. Yeah, so really this is split into 2 parts here, as I was just describing there. And I'm just going to move on to our first step here, of course, which is data decompositions and dimensionality reduction. So the overall class that's very common for performing dimensionality reduction is something called proper orthogonal decompositions. And for these methods, we'll have sort of a standard form that we'll follow. So for example, if you have data represented as X here, as this matrix, say you have two different dimensions, you have a time dimension and then a spatial dimension. The real purpose of proper orthogonal decompositions is to allow us to approximate a high rank matrix X by some lower rank matrix K, which allows us to extract information that might be ordered in a way that eliminates the noise, or at least allows us to reduce the effect that the noise has on our ability to perform that analysis. So in order to evaluate the effectiveness of these decompositions, we have a general form where we look at the norm of the matrix that is the difference between our original X or original data and then whatever our decomposition is, which we'll represent as this phi times A transpose. And so on the bottom here, let's see if I can switch over to a laser pointer. So on the bottom here, we can see that we can get a representation of our X using 2 other matrices. And the exact form of these matrices might depend on the method that you choose and what's specific about that. But what's important is, since this is a proper orthogonal decomposition, we enforce, or we really want the vectors of each of these matrices to be orthogonal to each other, so that we can get different modes of representation of this data. There are 3 main methods that are very similar to each other, but might be more applicable or might be vocabulary that you'd encounter in different settings. Those being SVD, singular value decomposition, PCA, principal component analysis, and then a more advanced one for dynamical systems called DMD, or dynamic mode decomposition. So we'll go over those 3 briefly here. So really what a lot of these practically are based on will be the singular value decomposition. It is an extension of the eigen decomposition, which is applicable for square matrices, but singular value decomposition can be extended to non-square matrices. Looks like we have you're okay? Okay. Something to note about the singular value decomposition is, because we are taking the square roots of the eigenvalues of M transpose M, as is the setup here, that actually will give us a symmetric non-negative, or let's see, a square symmetric matrix. And just for those people who do linear algebra and are familiar with this kind of thing, that is helpful because that ensures that those eigenvalues are going to be positive and real. So taking the square root does make sense in that case. Singular value decomposition is something you're more likely to see in that linear algebra context because it will have more of a geometric interpretation as opposed to some of the later methods that we will describe. But the idea behind this singular value decomposition is that you will turn your matrix M into this composition of these three different matrices, which will be the U, sigma, and V. And so we'll break down what each of those does here in a second. So those, the diagonal entries of your sigma matrix are going to be your singular values. So that's going to be describing the amount of stretching or the weight that you might assign to each of those modes, which are then captured by that U and V. V are considered the right singular vectors because they're on the right side of the sigma, and U are considered the left singular vectors. So really for a geometric interpretation, these modes are assigning to what degree you have a stretching or contraction within your space. So, and then to perform the dimensionality reduction, you can then say if this first, if I just want what's captured by that first singular value, I can approximate my matrix by taking only the first left vector multiplied by the stretching factor as given by the singular value, and then the row being the first column or first vector of V, but since we're doing transpose, then it turns into a row. That will ultimately give us a matrix that has the same shape as M, but compressed into a lower dimensional format. Similarly, as we continue to add dimensions, we just iterate on that as we go forward, or you can select some number, but this is how they multiply together to get a lower dimensional representation. To grasp some of the geometric understanding of what each of these components does, I have a video, like a little video that we can show here. I guess it's sort of circulating, so I'll wait till it gets back to the beginning because I couldn't control this. So for our matrix M, you can think it will operate, yes, sorry, question.
There's a question I can ask.
Let me explain real quick because I'm constrained by the video here. But you can think of a matrix M as operating on some space where it does rotations and stretching. And so I guess I missed it a little bit here, but you can think of each of these components operating such that, as we just saw with the V, what it's doing is it's operating on the output space, or sorry, on your input space where it's rotating it to align with a certain direction. And then the singular values, the matrix sigma that represents that, is going to be performing a stretching in that space along those singular values, or sorry, along those right singular vectors. And then U is going to transform back into sort of your output space, which is also a rotation. So because U and V are orthogonal vectors, because we need these to be orthogonal for this decomposition, that's why we're only getting rotation out of those, and the stretching is coming from the sigma. You said we had a question in the chat?
I mean, I think you kind of answered it, but does the stretching relate to the variance of the values?
Yes, and actually, that's a great question, which leads right into our next component here, because that interpretation of how we understand variance is more captured in this principal component analysis. So I'm guessing this is probably, of these terms, the most commonly seen among the members of this community, because instead of thinking it purely in a geometric interpretation that's more common for, say, people working in linear algebra, principal component analysis tends to have more of an interpretation when looking at the columns of your matrix as variables of a system. So really the idea behind it is that we're going to be reducing the dimensionality of our matrix, which in this case is a data matrix of our variables, while retaining as much variation as possible. So just as was mentioned in the chat. So similar to the singular value decomposition, our principal components are going to be the eigenvectors of the covariance matrix of X, which, if we refer back to sort of the previous slide here, or sort of reflect on what it was earlier, we were taking the eigen decomposition of our M transpose M. For the covariance, it's going to be very similar to that, except you then center that matrix in order to sort of set the mean equal to 0. That's how you transform into a covariance matrix anyways for that sort of computation. And then typically what will happen is we'll then project onto this new basis So say this example that we see here, they just find the first principal component, and then you can project onto that first principal component that will capture most of the variance or the majority of the variance in that data set. So we now have a lower dimensional representation of what's going on in the full data. Key things to note about our principal component analysis. The principal components themselves will be uncorrelated and they're ordered, assuming you're using like a software package that's typical for that. And then, as I mentioned before, this is the most common dimensionality reduction technique that you're likely to see when working with data or working with variables. There are lots of variations, by the way, on principal component analysis, but I'm not going to go into too much detail on that here because it adds, it builds on the same bones, but it might add some additional constraints that is required in order to encourage different types of solutions. And then once again, as a statistical interpretation, as I answered to the question here, this is going to be representing really the modes capturing the greatest percentage of variance here. So usually you'll see some sort of pattern where some small number captures a very large percentage of the variance, because many systems, physical and of the data that we encounter, really doesn't need all dimensions or even a large number of dimensions to really understand what the dominating variance is captured by. So I'll do a quick example here. Just this is sort of a common or canonical example for principal component analysis, which is, say you're starting with some image that is a full dimension, and it might have 780 by 1040 pixels, and each one of those in your data might be represented individually as, in this case, it's grayscale, so it would be represented by what the value of that pixel is, how dark it is. But we can then perform this principal component analysis on this image and then extract only a small number of the components here. The maximum number would be 780 because it's sort of the lesser of the two dimensions. And in this plot on the left-hand side, bottom left side, it actually shows, it's similar to the plot on the previous slide, except for now, instead of saying just what each individual contribution is, you're taking the cumulative sum over all of those. We're often concerned with how much variance can we, or how many principal components do we require in order to explain a certain amount of variance. So in this case, if our target is 95% of the variance to be captured, out of the 780 that are possible, only 38 of those, so less than 5%, are actually necessary to capture 95% of the variance. And you can actually see that captured quite nicely in the image on the right here, where even just 10 components gives us a pretty nice outline of what's going on. But once we up that up to 25, and even more so once we bring that up to 50, there's very little it's very hard to perceive the differences between 50, 100, 150, and 250, because effectively there's less than 5% of the variance that we're able to gain by adding those additional components. So that's really the power of PCA, and gives us the ability to really determine which modes are the ones that are most important. And just as an interpretation here, really what that mode is saying, when I say modes, what that's saying is we're looking at linear combinations of all the different variables that might be there. So a mode is going to be describing how much weight should I assign to the first variable versus the second variable versus all of these together. And so those modes don't necessarily say it's I take the first, fifth, ninth, and 10th, and then those are the only ones that matter. It's really more likely to be, I take 10% is coming from this one, and then 30% from this, and this one 10, and so forth, such that maybe it adds up to 100% of the value of that mode. But then when we reconstruct that and maybe take those percentages there, we can look at effectively what direction we might point things in as we take sort of partial contributions from each one. Okay. Any questions about PCA or SVD so far? I realize we're kind of moving quickly through a lot of these things, but I want to give a chance to move. Okay. So next we have, I'm not going to take too long on dynamic mode decomposition because this could probably be like 2 lectures in itself or something. But it is really, I want to use this as an opportunity to demonstrate how flexible these methods can be and how they can be repurposed for some really powerful computational techniques. So dynamic mode decomposition is really about, it's about working with data that has both spatial and temporal components that are coupled with each other, which is a very common thing in a lot of applications like that are often described as dynamical systems, or if you're doing things with like advanced partial differential equations, then this kind of thing might come up. A very canonical example, as I'll show later, would be with things like fluid mechanics. So the idea behind this is we're trying to approximate the function that describes how you get from one time step to the next time step. And so we are constructing this by splitting our data and effectively just creating two windows of data, where the first one is simply the entire, everything along the time step, all time steps except the last one, and then you're comparing that then to all time steps except the first one. So it allows us to do sort of a direct comparison where we are offset by one time step there. In performing this computation, we're effectively trying to approximate this function f that describes the full behavior of going from one time step to the next with some matrix A, which is really just a linearization of whatever that function would be. And so this would be common. Anyone who's worked with, taken maybe like an ordinary differential equations class, if you've ever encountered needing to linearize a system or taking like the Jacobian of a system, it's the same concept here, but just in a more computational framework. And so ultimately doing this, we're going to once again sort of have this similar setup where we're going to have two matrices multiplied by each other that have the same dimensions, but then we turn it into a square matrix by taking the transpose of one. And then I'm just warning everyone, I'm just going to glaze over any of the computational details because I don't think that's the focus here, but I just want to give a little bit here so that you can see that the steps sort of follow and can be simplified or seem very straightforward. Also to clarify, there will be times when I'll include some code on some of these slides here, and that's more just to demonstrate that there are some opportunities for, like, if you want to dive into it a bit yourself. But if you want more of like a practical emphasis and a bit more on the code and implementation of any of these things that I'm working on, my intention is for the fifth session to be more focused on software and how these kind of things would be implemented. So I will be distributing more details and more materials so that if people want to sort of test the waters on that front and figure out what kind of software you might want to play with before we get into those details, you can look forward to that. And hopefully, 8 weeks from now or so, we'll be able to do that in more detail. So really, once again, I want to come back. We're using the same bones that we have in many of the other methods where we are computing where we're performing a dimensionality reduction, we're finding what these dominant modes are, and then we're using those modes to sort of reconstruct the system and understand what is really explaining most of that behavior. So I want to give what I think is a really interesting and fun visual example of DMD, or dynamic mode decomposition, which is for fluid dynamics, as I was describing earlier. And I think this one just visually is really striking because it gives you a really nice illustration of what kind of things can be captured in these modes when you use this method. So if we see our example on the left-hand side here is looking at the flow around around some impediment. It could be like a ball in a fluid flow, and then it's leading to some vortices forming behind it, which might evolve over time as well in a very complex way. These kind of problems are well known to be quite complicated. When we perform dynamic mode decomposition on this data, we can extract a first mode, which seems to be quite straightforward and quite simple in that it's describing, in a lot of ways, just like the linear flow that emerges on either side of this barrier. And it really only has a real part here. So this left column is real part and the right column is the imaginary part. And you can see that really there's no imaginary part because this is capturing the linear flow, so it doesn't have rotations, since imaginary components of like eigenvalues are representative of rotations. However, once we move on to the second mode here, really what we're seeing is like what the symmetric, like the symmetric vortices that are forming, the symmetric components of the rotation that might pop up as a result of this impediment. So you can see, like, if we just divide it down the middle in each of these cases, we do have symmetry on both sides, and that helps us to explain even more of what's going on here, because as you might expect, there would be some symmetry to what's going on as the barrier itself is symmetric about that axis. And if we go on to the mode after that I'm showing here, this one's kind of fun and interesting, because now we're looking at more of an anti-symmetric mode, because we have sort of opposite effects happening on both sides, which we also see as being important in the data here, because both sides sort of have an alternating pattern as these vortices are forming. So this is some of the power of DMD, and really the explanation of these modes it can be understood more as these are like linear functions, which, as we take a combination of these together, help to explain what the full function is that is describing this behavior. Okay, I'll move on briefly now to a couple sort of simple clustering methods, or ones that are sort of built on the concept of clustering. So one that some of you may have seen before is called k-means clustering. This is what we'd call an unsupervised clustering method to take a data set of n data points and separate them into k separate groups. I'll describe what unsupervised means later, a little bit later in this talk here. But something to point out is that k for this k-means is something that we would define ahead of time in order to implement this algorithm. So as what's shown on the right-hand side here is an example where we set k equal to 3, and we're effectively assuming there's a simple barrier between these different sets, and then iteratively discovering what the most reasonable clustering is that takes place there. As this method is implemented, we will, in order to classify something into one set or another, you simply determine for each individual point which centroid, or effectively average value in the set at a certain point in time, the point that is in question is closest to. And so, for example, if I have maybe a set that's like in the top right corner, one that's on maybe the left side, and then one that's on the bottom right corner to start with, if I pick a point that is say right in the middle, but maybe a little bit offset to the bottom right, because it's closer to the average of the set that's on the bottom right there, it would be classified into there. But then once it gets classified into that set, then the average of that set will change, because it now incorporates that new point. And then as that update continues to take place, that will continue iteratively until there are no changes between iterations. And so you can see sort of how this might be visualized here is if you start with this blue, red, and green set, after one iteration, a couple of these points change over to the blue set because they're a little bit closer to the original average there. And then as you add those 2 points, this average will also move because it's added those. It also took 1 away from the red set. Similarly, each of those averages will have moved as a result of that too. And then once we do it one more time, some more points also get added to the blue, until after these really 2 steps, then no additional changes take place in this data set, and so we know we've converged. So that's one way that we can perform like a classification or a clustering without needing to know necessarily ahead of time what what class any of those individual points belong to. However, if we do have some additional information where we have some sets, subsets of data that do have predefined classes that they belong to, then as we add new data to that data set, we can then implement what's called k-nearest neighbors as a means to try and predict which set that belongs to. Did I see we had a question in the chat, by the way? Okay, I thought I saw a new message. So the idea behind this is that, once again, this K is something that we might define ahead of time. But what we're doing is we're looking at, in some radius, we could start that radius at 0 and then increase it until the number of other points that are within sort of the circle contained by within that radius matches the number of neighbors that we want to consider, our K value here. We then look at what is the, which class do the majority of the points that fall in that ball belong to? So yes.
Someone just asked, how do you know which K to use?
That's a great question, and honestly, that's a.
I think you should repeat the question. I'm not sure.
Oh, sorry. Yes. Thank you. Yeah. So I'll repeat the question here. The question was, how do you know which K to use? And that is a great age-old question that actually that in a lot of cases will be one of the biggest challenges of people working in ML, because that's what we call a hyperparameter, and it can vary a lot. I will say for for the previous example with K-means clustering, usually what you'd want to do is you do some sanity check afterwards to say, do 3 different classes make sense for this data set that we're looking at? Does it look clean? Does it look like there are maybe so many that are on this border, but intuitively look like they're actually separate from these other classes? So should we increase it? Or does it maybe look like we're introducing more than we need? That's unfortunately something that oftentimes has to come down to your discretion when you're evaluating this model afterwards. For K nearest neighbor, there's a little bit more of like a direct interpretation of what changing K does. Let's just take the extreme case where we say K is equal to 1. So all you care about is which point are you closest to, or the single point that's closest to you in your data set. And while that can be very useful because, oftentimes the nearest one will be informative on that front, but that could make it very difficult if you don't have a very clean boundary between your 2 sets, or if there are any outliers, or you have any sort of odd overlap that takes place there. So really what would happen is, as we increase that K, we are looking at a greater number of points, a greater number of neighbors, so that we're effectively smoothing out the barrier that would come between that. So I'll show an example here that I think is probably a little bit better of an indication than, oh, sorry, there's a question here.
Is there like a weighting in nearest neighbors where the distance to the nearest neighbor is also a factor, not just the sum of each other?
I am not aware of a named version of that kind of thing, but like I think that would be a very reasonable thing to try and do. That once again, that's another modeling question that you might have to answer is, how do you determine what those weights are? How do you penalize things being very close or far away? You could also say one potential challenge with that would be if you're right next to a point and that point happens to be an outlier, then if you are penalizing the distance between them, or penalizing greater distance, then and it's sort of like inverse to how close they are, then you'll sort of make it so that those being really close to an outlier could be worse. But in many cases that might not be an issue. But yeah, that's a great way to introduce maybe a slight wrinkle on this that might give you a little bit more complexity. That wouldn't necessarily do exactly what I'm saying, where you're smoothing out the boundary, because that would it would smooth out the boundary in a way because you'd still be considering more than one, but it wouldn't do it as sort of cleanly as just looking at everything sort of equally. But yeah, that's a very valid approach, and I think that would be viable. So if we look at this data set here, that's just sort of a toy data set that I created. I thought this one was kind of interesting because we have a few data points, say these oranges, that look like they should belong in the blue class, in class 0. But so if you were just trying to say, look at the first nearest neighbor, then you would need to effectively, if you look at like a boundary between where you'd label in each class, you'd clearly have like this first major boundary, which I think intuitively looks like it makes the most sense for this data set. That would be sort of between the bulk of these two subsets, these two populations. But then because we have these extra points, these other orange points that are sort of embedded deeper behind the blue lines, the enemy lines there, we'd sort of have these little balls in there that would be complicating that situation. And so you'd effectively have to account for those and have little areas there. Now, in some cases, you might have boundaries like that between classes, but let's say we're trying to make the assumption that these are, for the most part, well separable, then you'd probably want to have a simpler border. But if we increase that to, in this case, we're looking at 10 different neighbors. I've highlighted in red what 10 points would be under consideration that are closest to this black point. And you can see that it's sort of on this boundary, but looks maybe a little bit closer to these blue points. And there are 6 of the blue points selected and only 4 of the orange points selected. So then that are within those 10 nearest neighbors. So then this one would be classified as belonging in the blue class. Now this is just sort of like a simple classification method. If people have more questions, I'm happy to answer it about this, but I want to give sort of just a general understanding of like what's a first order kind of approach to answering some of these questions. So I want to move on now to the next sort of half of this talk, of this workshop, as we discuss more how to derive models from data. And so I'm actually going to focus on that last word here first about what types of data we might encounter. So there are really 2 major classes of data types. The first would be categorical data, which is generally going to be qualitative data that sort of fits into distinct categories, hence why it's called categorical. You might also call them classes. And then within categorical data, you have 2 different types. You have either ordinal or nominal. And that will depend on whether or not we have some hierarchy to how those classes are aligned. So I'll use the example on the right-hand side here of completely dummy data that I came up with. But imagine that we have data about commuting modes for how people get into work, depending on what their income level is. So if we look at this, the first set of categories here, which is simply what percentage of people use car, bike, public transit, or walking in order to get into work. This would be, this is categorical data because those don't really have like a numerical value to them, and they fall into sort of distinct classes that are independent from each other, that are separate from each other. And this would be nominal because there isn't necessarily an ordering of these, and each one is sort of equally different from each other. In mathematical terms, you might say that these representations are orthogonal to each other because they don't have an overlap. They're simply different ways to describe things that aren't necessarily directly related to each other. On the other hand, though, the other categories that we can isolate here, being high income, middle income, and low income, would fall under the ordinal, would be called ordinal, which we'd fall into that classification if the categories are on some sort of spectrum. And importantly, if sort of 2 categories are inherently farther away from each other than maybe some other combination of 2. So clearly here, a high income individual would be further away from a low income individual in this classification or in an understanding of this data than high would be to middle or middle would be to low. So those are two kinds of categorical data. And then the other type of data is numerical, as I somewhat alluded to earlier, which also will fall into 2 different categories. Once again, I have dummy data here, but just to serve illustrative purposes, and we can just view this x-axis here, even though really what I'm caring about here is is our counts of what's going on here. And then you can think of this as like an evolution over time, over seasons, as we're considering here. And so our first one would be discrete data, because I'm counting how many pets I might have played with over the past year, depending on what season I'm in. Clearly, winter, I'm stuck inside with a lot of people's, cats and dogs and stuff, which is very exciting. But during the summer, I'm active and and I clearly don't have enough friends who have dogs that they bring out. So that's kind of how that goes. But in any case, what matters here to determine something as being discrete is that those values take on specific countable values. So in this case, if I'm counting pets, I wouldn't say it can fall on some spectrum where I played with 3.64381 pets or something like that. I'd say I played with 3, and then I can only play with 1 more after that, 4, 5, 6, and so forth. On the other hand, if I'm instead counting how many kilometers I've biked in the past year, depending on what season I'm in, that would be continuous data, because the values that data can take is not constrained to some discrete number of points that it can be. Now, something that has sometimes confused people in the past is, well, I'm not counting kilometers by, on some actual, it's not like a real number where it can have an infinite number of decimals. Even if you have a limited precision or if you have finite precision to your measurements, because that data can take on continuous values, that would still be considered a continuous data or continuous numerical data. Okay, all set? Okay. Another consideration that I like to bring up when talking about how we model or create models for different types of data is what form that data that we're inputting into our model might take, especially if we're considering multiple variables. So many of the methods I was describing earlier, we were just saying, okay, we have one data set that all the variables are sort of within that same data set, or within that same sort of units, because they're maybe all neurons from, they're all neurons. And so we'd be measuring the same kind of thing. But that's not always the case. And probably in most of the work we do, it will be, but you might encounter that it's not always that. So if you have a single input data type across multiple variables, like we have on the top example here, where say, maybe you're generating a model where you're trying to predict how many resources you need to put towards maintenance of parks in Montreal. And you're like, okay, let me look at how warm and cold it's going to be on average across these months, and then we'll distribute our resources accordingly. If all you're considering is the maximum and minimum temperatures or the average high and low of across these months, those both are the same data type. And so they can sort of be treated on similar footing because you'll have those shared units. However, it could be a little bit more complicated, and you just have to think about how you'd build it if you have mixed data types, where instead you're looking at the high temperature as well as the days of rain, because a high temperature of 20 degrees is not the same, or like can't be directly compared to 20 days of rain in a month, for example. Those numbers need to be treated separately. And so that's just something worth considering whenever you're building your models, of thinking of what the form of that data is. There are also other considerations that you'll encounter more, and honestly, especially for a lot of the research that this community does, all of these will come up often. So you can have temporal dependencies or some temporal component to your data, which means that it evolves over time, and that relation across time is something that matters and is worth tracking. You might also have a spatial component that's going to be very common when you have any sort of like image processing, or within an image, you oftentimes don't want to just say, here are all the pixels, I'm going to just flatten them out and consider only what the values of these pixels are as if they're one vector. You often want to maintain what the spatial relation is across each of your, say, the pixels in your image that you're considering. But then in many cases, you'll encounter both. You need to both track or understand sort of the temporal dependence of your data, as well as the spatial relation, which can evolve over time. So that's a very common thing in atmospheric science when tracking, say, large weather systems or hurricanes. It's probably more, being someone who's American, right? Who's American, I probably hear about hurricanes a little bit more than we do up here in Montreal, but still something that is unfortunately something that everyone's heard about and experienced to some extent. And then, previously I was just talking about what type of input data we have, but then there are also some considerations about what the relationship is with what the output of your model is going to be. So sometimes you'll say you're working within some input space and then you're outputting something that's in that same space because you're trying to make predictions on maybe how that system is evolving. So an example I'm providing here is, say you're trying to use the scores of students across different grades within a year, and they have 2 tests they've already taken during the year, and you're trying to predict what is their score at the end of the year. Well, those are all within the same, that's all the same type, that's all the same space that you're working in. But that's not always the type of, that's not always sort of the type of problem that you'll encounter. Let's say instead you're trying to predict what the house price is based on some new house that just got built. And you have a large number of factors that might contribute to that. So maybe you're considering how large the house is based on square feet, number of bedrooms, bathrooms, appliances, school quality in the area, that kind of thing. None of those is in the units of price or anything like that. So that will sort of transform in a different way, and the model will need to be able to account for that and might sort of, as you design that, you gain things by changing types, but then maybe from an interpretation perspective, you have to be aware of the limitations of sort of working within such wildly different domains. And finally, worth considering for our output or target data will be whether or not that data has some label associated with it. So I referenced this a little bit earlier in the first half, but when we have labels associated to our data, whether that's going to be some sort of numerical labels associated for maybe like a linear regression task here, you can think of an input being, that's going to be like the X that we've been describing before. That's what you're starting with. And then maybe your prediction for the model that you created is going to be this red line here as a linear regressor. But then the output, our label, is going to be what the Y value is on each of those spots. So for a regression task, this would be often something where we consider it to have a label because for an input, we have an output. And so we can directly compare our prediction to that output, that label. Similarly, if we're doing like a classification task where we're asked, is this picture a picture of a cat or a picture not of a cat? Anyone who takes a machine learning course at any point, you've encountered either dog or not dog or cat, not cat. It's like every teacher's favorite task, apparently. But in any case, we'd have labels on each of these pictures, which we're assuming that these are correct labels because these will have been done manually before we feed it into the model as these labels. And just to note, labeling is often in the construction of many data sets is the most labor-intensive part of developing these data sets in a lot of canonical and machine learning examples. So it's really oftentimes big data sets being released is the precursor to new waves of methods being developed in machine learning. So one of the biggest data sets for image classification was released in approximately, I think it was 2013. And then a few more came right after that. And then that led to a very large wave of a lot of new methods that developed to work on that data set. And really that's why in the teams there was such a big explosion of AI. And then of course we have our unlabeled data, which since we don't have direct labels from this, what we'd really want to do here is try and extract those patterns that emerge here and then maybe evaluate it afterwards. Which, if this sounds a little bit familiar, that's because the methods we were describing earlier for dimension reduction or clustering using SPD, PCA are working with unlabeled data. So those would be sort of first order methods that you might use for that. So I want to give a quick overview to what the overall sort of outline or structure would be for how you'd perform a modeling task. As I just referred to, we'll have, first it'll be determined by to what degree our data are labeled. And that will tell us whether it falls into the unsupervised learning category, which means we have unlabeled data. So we can't use some sort of supervisor or some sort of like corrective method to directly compare our solutions. Or if we do have labels, then we can use supervised learning. When we set up a model, we'll have some kind of data that will be fed into this model, which to get some kind of prediction as given by this y hat. And this model can really be thought of as some sort of function or algorithm, which is operating on our input data x using these parameters which are outlined by this theta. So I'm going to use this notation just because this concept of theta and these parameters being what determine this function are very important for the development of these models and effectively the training, which I'll talk a bit later, but really that'll be the focus of the next workshop. And then I'll explain a little bit about what our different type of objective functions are for supervised learning, and then a very brief overview of how we might evaluate those models once they've been trained and how we'd structure our data to do that. So for unsupervised learning, let's say we have this very cartoonish data set that I've created here, where we have maybe images of 3 different types of things: acorns, apples, aliens. And then our model would then, because this is unsupervised, we don't know the answer ahead of time, it would have the task of finding some way to represent these different classes, these different input data, as in a space such that the ones that are most similar would be as close to each other as possible, and the ones that are less similar would be separated. So really, you can think of this as, this is like a toy setup for a model, but this could be sort of expanded to a larger class of approaches, where the objective of this would be to minimize distances within what might be identified as a class, maximize the distances across those classes, and then something that could be done sort of in what we call like an offline manner or outside of training would be then for us to determine what is the appropriate number of classes to label these different groups as. So like in an ideal scenario, it would be able to, sort of accomplish what we've done here, where the acorns are split up here, the apples here, and the aliens here, such that those are sort of separated in that space, and all of the ones that are in the same class are closer to each other than they are to the others. Of course, these are idealized situations, so they're not exactly going to show up that way in all the data, but that would be sort of a first order approach and something you might be able to accomplish with unsupervised learning. However, if we now go back, do a whole bunch of work, and look at every one of the images that we've been looking at and label them with what class they fall into, as I'm demonstrating with the colors here, then the objective of the model, instead of saying let me just output this as some sort of grouping or clustering without any prior knowledge of what these are supposed to be, I can split these up by predicting what class they actually fall into. So for example, if I'm given some input that to us seems very clearly in the shape of an apple, it might then give me a probability prediction of whether this is an acorn, an apple, or an alien. And since I'm trying to show this since the red is darker here, then it seems to believe that it's more likely that it's an apple than either of the other 2 classes. And so we would then compare this prediction to what our truth value is, which is a label. And in this case, the label is that it's a 100% probability that it's an apple, because we know that ahead of time. That was the purpose of the labeling, and 0% of the other 2. And so the idea is, because we know this is the correct answer, we can determine how far off it was from getting the exact right answer. And then through what we call training, we then update the parameters of the model so that its error on this sample is reduced. You can say it would be reduced all the way down to 0, but when we're looking at large data sets, we don't necessarily want it to be changing a ton every time it sees something. But once again, that's going to be something I talk about in more detail in the next one. So really the idea behind supervised learning and the objectives that we try to accomplish with this are we're minimizing whatever this loss is, whatever the difference is between our prediction and our label, and then some complications that can come up and things that when you're setting up a supervised learning task, you want to ensure that you can avoid overfitting. So making it so that you're only able to learn based on this one, based on like a small subset or one data point. which would allow us to maximize the generalization. So in order to evaluate these then and determine how to measure this difference that is between our label and our prediction, we use what's called objective or loss functions. The model or the function that we choose to evaluate this error is going to be dependent on your problem. And I'll just go over what they'd be for our sort of two primary classes of problems, being in the supervised category, being classification and regression. So for a regression task, I'm once again going to sort of use what would be a standard linear regression. To be clear, when I say regression, not all of them are linear. It just means that for some given input, I'm trying to predict what maybe the numerical output would be, but it's a lot easier to show linear regression than it is on any other kind of regression here. But let's say we have some linear regression model that we've developed, which gives us this red sloped line here. And we're comparing the error or the difference between our prediction and each of the true values that are assigned to each of these inputs. How exactly, so the difference between those we'd call the residual, and how exactly we penalize each of those residuals is going to be dependent on what function we use. And so there are a few different options here, and I'll show what the implications is for a couple of them. So the first one we can consider is mean absolute error, or MAE. It would be defined by this function here. We're effectively just looking at what is just effectively the distance or the length of each of those residuals. The absolute value of that, I'm just going to take what the average value is across all of those. So the contribution from each of these residuals or each of these errors is shown here by these black bars. You can see that small, effectively, all that's going to matter is sort of the base value, the first order of what that distance is. However, if we instead use what's called mean squared error, we are considering now not just the absolute value, but we're now squaring that distance. So what's that going to do? That's going to make it so that our larger distances, our larger residuals, will be penalized more than if you just take the absolute value. And those ones that are smaller, that are maybe closer to 0 or considerably less than 1, will be reduced even further, so they're penalized less. So what that turns into is, the ones that are larger become considerably larger, and the ones that are smaller and close to 0, there were only a couple, but they get even smaller. So really, you might wonder, why would I select MAE versus MSE or any other one? And that'll come down to what your objective is for your regression model. If you are looking at MAE, because that equally penalizes any distance incrementally, what that's saying is that being off by a small amount, if you're only off by, say, 0.1, increasing from 0.1 to 0.2 is just as much of an increase in what your loss value would be as if you increased from 3 to 3.1. So it makes it so that you're effectively trying to balance out the residuals that you're getting across all of your data points more equally. When you're looking at mean squared error, because it penalizes those larger values considerably more, it's trying to, it gets forced more to effectively reduce the effect of those outliers and make it so that effectively, like, those are accounted for more. Then for our other class here, of course, I have to use cats because that's our canonical classification example here. But the main distinction between classification task and a regression task in terms of how we measure loss is, whereas regression, we're measuring distances. We're trying to determine what is the difference, or what is the distance between my prediction and my label. Classification is more concerned is what is the difference between the distributions that are assigned to my label versus what my model is predicting. And so really it's going to come down to the concept of entropy, which I'm not going to go into too much detail here, but that's the foundation of what our equation is here. And we're looking at some predicted predicted distribution Q, and our true distribution P. And so I'll quickly go through this example just so you can understand. If we have a naive model that maybe has no information, so it whether determining this is a cat or a bird or a dog or a crocodile, it knows nothing, and so it'll just give an equal probability to all of those classes. If it does that, then it is being penalized not only for incorrectly assigning 25% probability to bird, dog, and crocodile, but also for saying 25 as opposed to 100% probability for the cat, because the cat is the true label as shown by the dark gray bar here. Maybe as that model gets a little bit better and can become a little bit more confident in identifying cats, then we move on to maybe a medium error situation where the bars for the incorrect are getting smaller, and importantly, the prediction for the correct label is getting better. Note that because this is better than, say, 50%, or really because this is the highest probability, if all you care about is saying, tell me which class is most probable, it would say cat here, even though the loss would still be quite high because of this big scary red bar at the top here. But if all you're measuring is, say, accuracy in terms of which class it says is most probable, it would say it's correct. But that's not necessarily saying that with a lot of confidence. And so that's another distinction that's worth thinking about when evaluating classification models. And then finally, if we have a low error model, let's say it has like a 95% confidence that this is a picture of a cat, that would be considered low error because there's very little to penalize. Okay, I'll quickly move on because I know we're reaching the end of our time here, but I keep talking about how we're evaluating these models and how do we work with these loss functions in the end. And in order to do this, we really need to start with which data we're going to be feeding into this model. So oftentimes when you're setting these up, the first thing that you need to do is you need to split your data set into your training set, which is what you're feeding your model and allowing it to update its parameters when it sees that to minimize its loss. But because it's directly seeing that, if you are reporting what the accuracy is and its ability to predict based on the data that it's seeing, that's very, if all you're reporting is what the performance is on the data that it's seeing and updating on, it's extremely biased because at some point it's seen it and tried to get zero error on that. So to really give a more robust representation of what the performance of your model is, you need some separate data set that it hasn't been able to see or it hasn't been able to update its parameters on. And that's the concept of having a test set. There is another way to do this using what's called cross-validation to sort of iteratively construct your train and test set. But I'm not going to go into too much detail on that right now because I know we're already getting close to 5 o'clock. And so here's my last slide here. Ultimately, when we're using this and once we've split up our train set and test set, when we go through the training procedure, which, like I said, will be the main focus or much of the focus of next week or of the next session 2 weeks from now, we'll want to track how that loss is evolving over the course of that training. But we need to do that not only with our training data, our training set, our training loss, but we also need to keep track of that for this test data. And that's where we tend to fall into 3 different regimes of training very commonly. We'll start when there's very rapid changes as it's sort of learning the first order patterns that are necessary to perform this task, which is during this underfitting mode, where the loss is still rapidly decreasing as the model is learning based on seeing more data and iteratively decreasing its overall loss. And then maybe there will come a point where the rate at which the loss is decreasing on the training set is starting to slow down, but will usually continue to decrease because it's sort of fine-tuning those parameters over and over. But then once you get far enough, as anyone when looking at sort of your classic examples of, say, polynomial fitting, you'll find that if you have n data points and you choose a polynomial of order n, and you're trying to predict what the data is there, you can fit it perfectly. You can get your loss down to 0. But as soon as you try introducing a new data point that you definitely haven't seen before, in all likelihood, you just completely overfit your data so that your prediction on that is much less likely to be accurate. So you want to avoid that, and your way of measuring that is really by tracking what your test loss is by having that separate data set. And I just want to clarify, because I've been saying, like, you don't want your model to see the test set and update its parameters. So when you're evaluating on the test set, you can use that to get some sort of descriptive statistic or descriptive value to say what the loss is there, but it's outside of the training procedure. So when it sees it, it's not going to be updating its parameters on that. So that's really the distinction there between how you're utilizing the train set and test set, even if your model is, because I'm like, oh, my model is seeing my test set because I have to evaluate every epoch of training. But because it's not actually changing as a result of seeing that, it's not like that is biasing the results of your model. So that concludes the slides that I have for today. And I know we're sort of reaching the end of the time here, but I definitely want to open up the floor for anyone to ask questions about anything that we've touched on today.